In this video, I'm going to talk about momentum and impulse. This is the first video of the momentum and impulse unit, and these are the learning objectives for that unit. So we want to understand the definitions, look at different types of collisions. We want to be able to approach problems by using either what we know about impulse or what we know about conservation of momentum, and we want to be able to answer basically any types of questions that we might be asked. All right, let's start with a definition of momentum. Momentum gets the symbol lowercase p, and it has a hat on it, and that's indicating that it is a vector. And momentum is the product of mass and velocity. And you can see that momentum and velocity are vectors. And since they're vectors, and they're the only two vectors in that equation, they're in the same direction. All right, so what units does momentum have? Well, we know the units of mass are kilograms, and we know the SI units of velocity are meters per second, and so momentum must also have units of kilogram meters per second. Both sides of an equation must have the same units of kilogram meters per second. Momentum is a fairly intuitive concept, and so I'm not going to spend a whole lot of time. We're just going to go ahead and get started looking at an example here. We're going to rank these different cases from the least momentum to the most, and so we can simply calculate each one. All of them are going in the same direction, and so we just multiply these together, and so we can say 10 kilograms times 2, we get 20. We'll just write that this is the momentum, and I'll put the units up here in the column header. That's 20 and 24, 20, 40, and then this one, even though it has a lot of inertia, it does not have any momentum. And that is one area where students sometimes get confused, is the difference between momentum and inertia. And so we can look simply at this column to figure out how much inertia each thing has, but the momentum column comes out, the rankings for this come out significantly different. And so case 5 has the least momentum, and then cases, let's see, 1 and 3, and then case 2, and then case 4. Okay. Now we'll look over here. Which of the following represent a change in momentum? And then for each of the scenarios that does represent a change in momentum, let's see if we can identify what force is causing it to change its momentum. Alright, so there's a car which has some mass, and it's slowing down from 50 miles per hour to 40 miles per hour, and that is definitely a change in momentum. Well, what's causing that car to slow down? Probably air resistance or some internal friction. And so for simplicity, we can say the force of air resistance. Okay. A ball that's traveling at 20 meters per second to the right, and then it hits a wall. Now it's going 20 meters per second the other direction. Did it change its momentum? Well here, if we were to calculate it, we would get the same number either way. But remember that momentum is a vector, and so at the beginning it had a momentum to the right, and afterward it had a momentum to the left, and those are two different things. So it did change its momentum. And what force caused that? What pushed on this system? The system is the ball, and it was the wall that pushed on the ball. Alright. Case C, a car is moving at 20 miles per hour west and is struck by a truck that is going the same direction, and so the car speeds up. That's a change in momentum, and that was caused by the force of the truck. And then in this last case, the car is going 40 miles per hour but then takes an exit ramp. It's still going the same speed, but it has changed its direction. So just like in case B, we have a change of direction. And this, if you recall from chapter 6, this would be caused by the force of static friction. Remember, that's a lowercase f with a subscript s, different than what we saw in the last chapter, which is capital F with the subscript s, which means the spring force. All right, now let's talk about impulse, something that's not as intuitive. An impulse is equal to the change in momentum. And since momentum is a vector, that means impulse is a vector. Some textbooks will use the letter J to represent impulse. Your textbook, the OpenStax textbook that is, does not. They just use the symbol, or they just write the word impulse. Okay, the OpenStax College Physics textbook. All right, but impulse is also equal to the net force times the time that that force is exerted for. Okay, so we have these two different ways to think of this. Okay, so it is equal to change in momentum, which we could write as P final minus P initial. Remember, delta always means final minus initial. Or we could write this as mvf minus mvi, assuming that the mass stays the same, which is pretty common, and I think that'll be the case for all of the examples that we'll be doing in this unit. All right, so there's these two different ways to think about impulse. They're both correct. And we can see that impulse is not equal to force, that impulse and force are two separate things, and we need to, well, here's an example that will allow us to understand that a little better. So I have a person that falls 90 feet, and then they land on the sidewalk. Certainly not a good thing for that person. And so as they're falling, they're speeding up, and they're going a certain speed. They have a certain speed right before they hit the sidewalk. Okay? You might be tempted to call that V final, but I'm going to call it V initial. Because then, just after that, then they hit the sidewalk, and their V final is actually 0. And then we have somebody else who falls, and they are going the same speed just before they hit the sidewalk, and then right when they hit the sidewalk, they slow down and they hit an awning. Sorry. So this first person hit the sidewalk, this second person hit an awning. But either way, they're both going the same speed when they are about to collide with either the sidewalk or awning, and they're both going the same speed afterward. And so both of the objects had the same momentum, okay? They had the same velocity, and since they're the same, it's the same person, it has the same mass. So the momentum is the same before and after. And since those are the same, then delta P must be the same for both. So the impulse is the same for both. So they both experienced the same impulse. However, one of the people lived and one of the people, well, it doesn't say, but most likely did not, or certainly sustained a lot of injuries. Why did one person sustain a lot of injuries while the other person did not? And, if they had the same impulse, why the difference? Well, it's because of the force. And why was the force different? Well, if we think about the sidewalk, when you hit a sidewalk, you're going to come to a stop very suddenly. And when you hit the awning, it's still going to be a fairly sudden stop, but you're going to stop over a greater amount of time than when you hit the sidewalk. And so for the awning has a larger delta t, which makes the force smaller. And if we look at this equation, if we rearrange it, F net is impulse over delta t. So we can see that dividing by a bigger time is indeed going to give us a smaller force. All right, and here's an example of an ostrich egg hitting a wall and stopping, or an ostrich egg hitting a sheet and stopping. And this is a demonstration that I usually do in class, and so I'm not going to be able to demonstrate that for you right now. But you can look up videos of eggs hitting a sheet versus a wall, or a water balloon or something like that. There's definitely videos out there on that. And so then we can calculate the impulse for each egg. So this is really just the same as the last example, except that here we're going to do the numbers to actually calculate what it was. Okay, so impulse, if we went with trying to calculate it as force times time, we wouldn't have enough information. But if we do it as change in momentum, we do have enough information. 0.5 kilograms times, what's the final velocity? 0 minus 0.5 kilograms times 14 meters per second, and then that's equal to negative 0.7 kilogram meters per second. So I should have said that our VI was equal to 14 meters per second to the right, and defined to the right to be our positive x direction. And then here's our sheet or wall that we're running into. Okay. And we don't need to do two calculations because both eggs had the same mass and we're going the same initial speed. Now, if the time of impact, the time it takes for the egg to slow down against the wall and come to a stop is 0.1 seconds, and then it takes 5 times longer for the egg to slow down against the sheet, then we can find out what the average stopping force is. Because, as I showed you on the last slide, impulse equals F net times delta t. And then we can solve this and we can say F net equals impulse over delta t. And so for the egg hitting the wall, simply negative 0.7 kilogram meters per second divided by 0.1 seconds, and then that is going to be negative 7. And then if we look at the units, kilogram meters per second is negative 7 newtons. Alright, but the one for the sheet remember, same impulse, but we divide it by 0.5 seconds. In this case, 0.7 divided by 0.5, we get negative 1.4 newtons. So we can see the one that hits the sheet is going to experience a smaller force. Now about this negative sign, the negative sign is the direction of the force, and it makes sense that the sheet or the wall would be pushing in the negative direction. Alright, and I'll pick up here in my next video.